the title of my presentation is the non-autonomous linear quadratic non-cooperative differential games with continuous updating. So here I will describe briefly what is the class of games with continuous updating. Here I will present and I will try to describe what is the non-autonomous linear quadratic game with continuous updating and present some convergence results. Before I start, I'd like to add some few words about the motivation for the work on the continuous updating approach. So this is the title of the presentation of my colleagues in my presentation. Sorry for this strange thing. So my colleagues, they are working on the differential game-based driver system for different things, such as this special case, this case of fuel optimization, fuel consumption optimization. Okay, so the idea of their work is that they are building a driver system which is based on the differential game framework, in particular on the linear quadratic case of it. And here this framework or this game is a game of two players. So one is the automation, another one is a human, and it is assumed that the automation knows the objective function of the human, and then during the game, at every current time instant, when the assisted driving system actually works, the system or the automation uses strategies or controls taking into account possible strategies or controls of the human. But what is important here? The important thing is that at every current time instant, human or a driver, when making his actions, orient himself on some fixed time interval, t dash, which we will call later information horizon. So he cannot, as in the classical differential game literature, take into account all information that it will be available to him from the current time instant t to until the end of the game, large t, or to plus infinity, or to some random horizon, this kind of. So in this particular situation, what he has at every current time instant t some truncated information about the game. So this is the motivation for the continuous updating approach that I will present a little bit later. So now about the non-autonomous case. So on this slide, you can see the initial model of linear quadratic differential games for the non-autonomous case. What means the non-autonomous and why I especially say that in here, why I highlight this problem. So this model is described by the motion equations 1 and payoff function 2 for each player, for player I. And what is important here? The important thing is that the matrices A, B1, etc., Bn, and R, Ij are functions of T. Well, this is very easy. This could be understood as a simple refinement of the model for the linear quadratic case, but for the continuous updating approach, this gives much more interesting information, much more insight. Later, when I will explain what is the continuous updating approach, it will be easy to understand. So we have classical assumptions here that matrices Qit and Rijt are symmetric for all t from t0 to large T, and Rii is a positive definite on this on the interval from T to large T. Okay, let's move on. So as a solution concept, we want to use a feedback Nash equilibrium with the classical solution represented here. But what is the continuous updating approach? So in continuous updating approach, we suppose that at every current time instant t, all players in the game have information about the motion equations and payoff functions only on the interval from t to t plus t dash. It means that when the current time instant changes, current time instant t changes, the information also changes according to this time interval. And of course, the current time instant t changes continuously in time. And our goal is to define a concept which is to define a Nash equilibrium or a related concept that could be used as a Nash equilibrium in this game. But the problem is that for this class of games, we would want this Nash equilibrium to be Nash equilibrium at every current time instant t. We want it to be at every current time instant t, the first point of the Nash equilibrium defined in the interval from t to t plus t dash. But the problem is that when the current time instant t changes from t to t plus epsilon, for example, the interval on which we want to find Nash equilibrium also changes. So it means that the concept that we want to define actually is built out of the is a composition of first points of Nash equilibriums for all possible current time instance t. That is why it is could be a little bit complicated and also interesting. Okay, so on this slide you can see the model of the non-autonomous linear quadratic differential game with continuous updating. It is defined by the system of motion equations 4 and wave functions 5. Here, what is important? The important thing is that you can see that the current, the state x has an index t, and also the control has also an index t. Why? Because the game which is presented now on the slide defines the behavior of players on the interval from t to t plus t dash. It is defined as a, this model defines a family of games on the interval from t to t plus t dash. But when t changes, all the solutions such as corresponding UTSX and XTS also are changing. Also, you can see that the initial point of the motion equation 4 is x, which is which could be any variable. Yep. Okay. Yeah. So the next thing, as you have seen from the previous slide, for every current time instant t, we define our own strategies. Yes, and we define strategies from the interval from t to t plus t dash. But how to compose the strategy profile that will eventually take place in the game? Of course, we can consider it as a game on the interval from t to t plus t dash, but what we're interested in the outcome. So on the slide you can see formula 6, which shows us the strategy profile that will take place in the game. Of course, we cannot assume any good properties of the existence of UTX in the formula 6. For the general case, of course, we cannot. But for some special case, we can say that it can be continuous, it can be unique, and we can show the existence. Yes, but for the general case, of course, even if we can assume the existence of UTSX for every current time t, we cannot assume any good properties for the resulting function UTX, because of course it can be composed, it can have infinite jumps, then this is not what we are actually interested in. Okay, then how to define the trajectory which will correspond to the strategy profile UTX. We just simply need to substitute into the motion equations 7. So what is important? Why we need non-autonomous case? Why we need a dependency upon t in this matrices in the matrices on the in the pair function of player I? So if we assume that the model is autonomous, it would mean that the game actually repeats step by step. So it means that we have the same game all the time. The motion equations are not changing. The pair of functions is not changing. The only thing which changes is the x, the state. The state changes, and according to the state, we use some, the players use some control, which in some sense is not a very interesting case to consider. What is interesting is to model the behavior of players, assuming that players at every current time instant t obtain a new information, that they update their information about the motion equations and about their pair functions, obtain the information about their new preferences and the preferences of other players. So you can imagine that at the current time instant t, this matrix, the dependency of this matrix upon the current time instant t changes. So, so the modeling could be different from the autonomous case, but this I will show in the simulation example. Okay, so how to define a concept of a Nash equilibrium in this game? So the classical definition of Nash equilibrium is not suitable for this case. Why? Because the players do not have full information about the whole interval which the game is defined at the very beginning of the game. So we cannot compute the payoff of players on the whole interval and then use a classical definition and compare whether the individual payoff of player I would be more than and so on. This case is not suitable. What we can do is we can introduce the definition which is presented here on the slide. Sorry, there's a mistake. We only focus on the feedback-based Nash equilibrium. So, okay, let's move on. And what you can see now on the slide is are the sufficient conditions for the Nash equilibrium in the non-autonomous linear quadratic differential game with continuous updating. Okay, of course, for the feedback case, it's possible also to derive a formula for the open loop based Nash equilibrium for the autonomous case as well, but it was done in other papers, so I did not provide the results here. Okay, so for n, this is the result which is true for n-person linear quadratic non-autonomous differential game with continuous updating. If the solution of a system of Riccati differential 9 exists, then the linear quadratic differential game with continuous updating has a linear feedback Nash equilibrium in the form 10. Okay, what is important? The important thing is that the system of Riccati differential equations 9 is defined not for the whole interval in which the game is defined as it usually is for the linear quadratic game models, but it is defined for the interval from 0 to 1, or you can say from t to t plus t dash, which actually which already represents of how already is enough for the solution, already represents all dynamics in the game. So we need to solve this Riccati differential game only one time to obtain the Nash equilibrium. Okay, next important thing is that...
Sorry, yes, can yes? The mathematics is getting very heavy for me, but let me ask you an intuitive question which will help me.
Yes.
You see, at time 7, I can only look forward to 7 plus t, yes? But I also know that if once I move a little forward, I'm going to get more information. So am I foreseeing the fact that I will keep getting more and more information and taking that into account when I take a decision now? Or how forward looking am I? Or how myopic am I? Is my question clear intuitively?
Yes, it's very clear. So actually, my work is only the beginning for the class of games with continuous updating. So actually, the model is could be understood as a simple one. So at every current time instant t, players only look ahead from t to t plus t dash, and they do not know what goes after t plus t dash, and they do not think they will know what will happen after t to please tablet.
So they are quite myopic. They are not forward looking about the fact that they will get more information. They are really myopic.
Exactly, yes, yes. But sometimes the simplification can give us good results, because as I think in the real life, actually what you do is you behave myopic usually. But it depends on the person, of course.
At least I do behave myopically. I agree with you.
Yeah, but it's very good, a very good comment, because I also, if I want to develop this approach, that I need to take into account all these things, and I'm very thankful for the question. It's a very important thing. So
one is a somewhat related question. This is also known as in the literature moving horizon optimization, or moving horizon games, where you look, I mean, you can even have a single player version of this, like a government is making coming up with a policy, and you make a 4-year plan, and then you implement the first year's plan, and then during the second year you go back to the table and then see whether you can improve upon that, looking at the 4 years ahead of you, and then again implement only the first year of that 4-year plan, and then so this way you can continue, and this has been viewed as an acceptable way. Of course, the planning horizon could depend on how much you know about the future. And this is a quite a valid approach, especially if you don't have perfect knowledge until ad infinity, and so therefore you are restricting your planning to a much smaller interval, but moving it forwards. So that's why it's called a moving horizon strategy design, or moving horizon optimization problem. The case when you have multiple players, then the question is whether all players go with the same length of the horizon. There has to be an implicit tacit agreement among the players, even though it's a non-cooperative game. There has to be an agreement that they are all using the same length of the planning horizon as they move ahead. And this is, you are making that assumption in this case.
Was it the question, or should I?
No, well, it was a comment and a question. The comment is, this is known as a moving horizon decision-making problem, with a single decision maker as well as multiple players. But then my question is, your assumption is that all players have exactly the same.
But he has only one player, one human, and the other thing is a machine robot.
No. I can comment on this. So here, the machine and robot was a motivation for this work. If you want to know about that part, I can give you a link to a recent paper on IFAC 2020 about the inverse optimal control with continuous updating. There we apply this technique. Here it's only it is a differential game model for n players.
For n players, so therefore my question is a valid one. The underlying assumption is that the players have exactly the same length of the planning horizon, the same planning horizon. Now, if they do not, then the problem becomes much more complicated, and even at the conceptual level, whether it can be formulated or not is a question.
Yeah, so actually here, T dash is equal for all of the players.
Right.
It is the same. And well, as I said, this is the beginning of this work. So there was no need to make it, to overcomplicate things. So the main idea is to model the behavior of players when they use in this continuous updating approach. For the moving horizon or rolling horizon problem, so actually I was searching for that direction before. I did not find actually a clear problem statement, clear results for continuous updating case. Only what I found for the optimal control is a stabilizing control for the linear quadratic, kind of linear quadratic stabilizing control. But the key point is that, well, if it's stabilizing control, then there's only one objective function on one hand. On the other hand, the key point, the idea is very different. You need to stabilize the system.
Yes.
Here we want to model the behavior.
If there is a single controller controlling a system, that is the main goal, to come up with policies, simpler policies, which would lead to stability of the overall system. But of course, that is not an issue here because you have stability is not one of your goals.
Mm. If you could recommend me a paper for moving horizon,
I'll send you some literature. Sure.
Yeah, if there should be something for continuous updating, I would be not continuous updating, for continuous.
Of course, there's also the discrete time version of that. You have a discrete time dynamic game, in which case it makes more sense because when you are talking about planning horizons, you have it in terms of sort of days or weeks or even years, and so therefore everything is an integer there. So anyway, please go ahead.
Yeah, okay, thank you for the comment. So another important and could be an interesting thing is that in the form of the Nash equilibrium, feedback-based Nash equilibrium, the formula 10, you can see that it depends on the solution of Riccati differential equation, but only at the first point of the solution. In the classical linear quadratic optimal control or Nash equilibrium, the dependency is on the on the whole solution of the Riccati differential equation. Here on the system, but here is only on the first point, the point where at the point 0. That is an important thing, which shows us that actually when horizoning is moving continuously, we only take the first point every time. Okay, so yeah. So another interesting thing that we wanted to show is that we wanted to show the correspondence of the continuous updating case and a dynamic updating case, or maybe a moving horizon or some discrete moving horizon case. So what you can see on the slide here is the definition for the model with dynamic updating. It is almost the same as the definition for continuous updating, but what you can see is that the updating goes in the fixed time instance t0 plus j delta t, and players at every current time instant t have information about motion equations by your function, the interval from t0 plus j delta t to t0 plus j delta t plus t dash. And updating comes into the fixed intervals, but this is not the most important thing here. So according to this model, we can define Nash equilibrium, or the resulting Nash equilibrium, that is constructed almost in the same way as done for the continuous updating approach. And we can also provide the form of the Nash equilibrium with a dynamic updating, feedback-based Nash equilibrium dynamic updating for the non-autonomous case. Yeah, and what I was what the most important thing that I wanted to present is that when the updating interval delta t for the discrete, for the dynamic updating case converges to 0, then the Nash equilibrium with continuous updating uniformly converges to the Nash equilibrium with Nash equilibrium dynamic updating uniformly converges to the Nash equilibrium with continuous updating. Of course, several conditions should be satisfied for the matrices RII and BI, and also some conditions should be satisfied for the solution of the Riccati differential equation. But the main idea is that when the length of interval delta t converges to 0, the dynamic updating converges to continuous updating, and that's what I hope we will be able to see from the model example. Of course, this is all true for the linear quadratic case. For more complex cases, much harder to derive. Okay, so the next result is related to the trajectories. So the trajectory, generally trajectory with dynamic updating converges, but not converges pointwise, converges to trajectory with continuous updating as the updating interval converges to 0. Of course, the same conditions should be satisfied. But let us consider the example. So let's consider the example of modified differential game of investment in public goods. So we have the payoff function of player I18 and static or motion equations 19. You can see that we have the parameters or functions which represent the non-autonomous case. And here you see T, this kind of functions. So let's move on. So on the slide, you can see the solution for this specific game model. This is the Nash equilibrium with continuous updating, which was obtained using the sufficient conditions presented before. And then we can obtain corresponding trajectory by substituting this Nash equilibrium into the state equation. I do not show the technical details here. Maybe the time is not enough. Okay, so what we can see here on the slide is the comparison of the Nash equilibrium with continuous updating and Nash equilibrium with dynamic updating for a specific case of several updating instances. So you can see that the trajectories and the strategies are not quite the same. But what happens when the number of updating instance or the value of updating interval converges to 0? We have the convergence. There's the two theorems before we're showing that. Another interesting thing is to see why the non-autonomous case is important, and if the solution for the autonomous case and non-autonomous case are the same, because otherwise why to present a special, why to build a special presentation, a special paper for the non-autonomous case. So what you can see here on the slide is you can see the comparison for our specific model example for the case where the non-autonomous part becomes autonomous when we say that T in the formula 20, when T becomes T0, when we fix T here in the non-autonomous part, what happens is we can see the comparison here. So you can see that the Nash equilibrium is actually different. and the motion, the state equation is also different. Another important thing that maybe is missing here on the slide is the slide which shows the comparison of the solution of the initial linear quadratic differential game model and game model with continuous updating. Of course, the difference is very easy to see. I did not present the slides here, but at least you could see it from the Formula 10. Another important and another important point is that the theorem which is presented here on the slide also presents the necessary conditions for the case of two players, and another interesting thing is that if we consider an autonomous case, and we consider a case of two players, then we can automatically say that the Nash equilibrium with continuous updating for this specific case would be unique and continuous. Yeah, but this is a small result which is not very general. That's why I never added it to the presentation. So still there is an open question of what are the properties of the strategy profile UTX here, when it exists, when it is unique, and so on. Okay, so thank you very much for your questions. If you have any more questions, I would be very happy to answer, and if you have any suggestions as well, I would be very happy to communicate on that.
Ovanes.
Yeah.
I recall that Bram van den Broek did also something on moving horizon control in dynamic games. That was in the Journal of Economic Dynamics and Control in 2002. So maybe you could have a look at that. Huh?
Okay, thank you. It was dynamic or differential? Usually...
dynamic. Moving horizon control in dynamic games. But it was also in a continuous time setting.
Okay, thank you. Actually, I would write you an email with the question so that I do not miss anything.
Yeah.
Thank you. Maybe you have any kind of suggestion about how to study the uniqueness or for the specific case, or maybe it's not.
I would have to have a more detailed look at everything, what you did up to now. Yeah.
One quick question for the scalar game, scalar dynamics, which was in your example. You were able to solve the Riccati equation, and for each horizon, and now it's the value of z at 0 that is relevant. And of course, if you can solve for z explicitly, then you can compute that value. Now, what happens in the more general case, like if you have a vector version, where it's almost impossible to solve z explicitly. You can do it numerically. And my question is, of course, all you need is the value of z at the endpoint. I mean, these are equations that move backwards in time. So therefore, you have a specific boundary condition at 1 or at capital T, and then you go backwards by an amount t, and then you solve it you are looking for its value if you shift the interval at 0. So my question is it possible to compute the value at 0 without computing explicitly the solution of the Riccati equation? because that's what otherwise computationally it's not efficient.
Yeah, it's a good question. I never considered whether it's possible to get Z0 without solving the system of Riccati differential equations. Maybe your question contains an answer simultaneously.
No, it doesn't.
I need to think.
I was curious because otherwise it's a computationally, it is for the infinite horizon problem, for the continuous time problem, you are essentially going, as you move t, you are going to solve essentially a continuum of such equations unless you have a time invariant problem. In other words, if the coefficients like a and b and so on are functions of time, then you have to solve a continuum of such equations, which is quite infeasible. Whereas if they don't depend on time, the state dynamics, if they are time invariant, then you solve only one Riccati equation, as you also indicated, and over the interval 0 to t, and because the system does not change over time, and then you use that solution at 0, you solve it only once, and then you use that in your policy for the players. But if it is if it's a time variant system, then it may be more difficult to obtain the solution. Do you have any comment on that?
Yeah. So, well, for the model example that we have considered, of course, it was possible to obtain an explicit solution, though, so we kind of skipped that problem. But well, sometimes it is possible to use a special substitution to change the non-autonomous case to autonomous. So sometimes it is possible to change the model into, then this approach still works. For the numerical approach, well, in this work, I do not present how to do it, and I think it's a subject of a future work, but I think it's still possible to do because we do not consider it as an interval from. So t is a parameter. Is not. Well, I need to consider this.
Yeah.
I think.
Yeah. Okay.
Yeah, but that's a very good point. I think you're. Yeah. Yeah, but the main idea is that the main advantage is that you only need to solve the system 9, and then you can model the behavior of players such as when the information updates continuously in time. You do not need continuously recalculate the solution. But yeah, when it is impossible, then it's quite complicated. Also, in the stream of these papers, there was the system of Hamilton-Jacobi-Bellman equation, which is also suitable for continuous case, and the Pentragen maximum principle. So there could be alternatives to these approaches as well. But yes, your question is I think very important. It should be taken into account.
Okay, thank you.
Thank you very much. If you have any more questions, I would be happy to answer.
Okay, Ovanes, may I ask one?
Yes.
Just regarding expression 10. So you have a finite horizon game, right?
No, actually, I do not specify the horizon. Because the only thing which is the only horizon that I consider is from from t to t plus t dash. So for every current time instant t, we look ahead for t dash. But actually, the Nash equilibrium or the strategy profile 10 can be applied for closed time interval, for infinite time interval. It doesn't matter actually.
Actually, when the duration of the game is infinite, so maybe my question is not relevant. But when the duration is finite, so something, well, it might well happen that the horizon, the updating horizon, is larger than the number of stages left, right? And well, from my perspective, it seems that players should, well, account for the remaining number of stages, so the remaining period of the game. But well, in 10, when in expression 10, there is only t dash, right? So, well, I think in this expression, so this is the equilibrium action for any t, right? So even if the number of stages or the time is less than capital T, so this is something which is, I think.
Yes, I clearly, it's a very good point. Yes. So here, I did not add any additional condition of when t plus t dash is less or equal than large t, when large t defines the length of the game. So I did not add this condition, but of course it can be taken into account. Then the theorem, which on this slide would be divided into two parts. So when t is less, then large t minus t dash, and then when it is more.
So when the game is when the game has an infinite horizon, so this actually comment is not relevant, because for any time instant, capital T dash is less than the remaining number of stages for the remaining time. So, but for finite horizon game, it must be somehow the player should account for the remaining number of stages.
Okay. Thank you very much. Yeah, it should be elaborated as well. Yeah, I guess. Okay, so do you have any more questions, or? If you don't have any more questions, then I want to say thank you for participating in the online session.